All right, hello and welcome. This is going to be our homework help video for the Unit 5 Radicals review. Let's get started right now with problem number 1. Simplify the cubed root of 32. One way to simplify cubed roots is by employing just a list of cubed numbers. So I might just create a very short list of numbers and what they are cubed. 2 cubed is 8, 3 cubed is 27, 4 cubed is 64. I'm already above 32, so I don't really need to go on. And then I just look in my x cubed column here for the biggest number that will fit into that 32 evenly. I only have one choice, it's the 8. And so I'll split the 32 into an 8 and a 4. So this cubed root of 32 becomes the cubed root of 8 times 4. I can now distribute that cubed root, make this the cubed root of 8 times the cubed root of 4. Cubed root of 8 becomes a 2. Just look back over here because 2 cubed is 8. Therefore, the cubed root of 8 would go back to 2. 2 times the cubed root of 4. There's no more perfect cubes in the radicand there, so we can box it and move on. Problem number 2, I might use a different method. I call this the jailbreak method, where I take the number inside and I factor it completely. So 48 can be split into a 2 and a 24. 24 can be split into a 2 and a 12. 12 could be split into a 3 and a 4, and the 4 could be split into a 2 and a 2. So I'm going to rewrite this, and instead of 48, I'm just going to write multiplication of all of the end factors of all of these branches. 2 times 2 times 3 times 2 times 2. And for the m to the 4th, I'm going to write out m 4 times. Now this is a square root. So to break out of a square root, you need to make groups of 2. There I can make a group of 2, and a 2 can jump out. Make another group of 2 here, another 2 jumps out. And I can make 2 groups of m's to have some m's jump out. So let me write this a little differently. So a 2, an m all jumped out, but the 3 got left behind. And then I recombine everything that's outside to make this 4m squared square root of 3. My final simplification. All right, let's take a look at number 3. We can only combine radicals if the radicals match. None of these radicals match. So our only chance to simplify this is to get those radicals to match. They'll have the same index, so that's good, but the radicands are different, so we need both of those things to match. But if I look at 24, I might think, well, I could pull a 4 out of 24 and rewrite this as the square root of 4 times the square root of 6 minus 3 root 3. That can't be simplified. And 27, well, I can pull a 9 out of 27, make this the square root of 9 times the square root of 3. Simplify the square root of 4 to become a 2, so negative 3 times 2 root 6 minus 3 root 3, and the square root of 9 to become a 3 minus 3 root 3. This one won't be able to combine with these, but now these are both square root 3s, so we can just combine the number in front, sort of like coefficients. Combine these numbers here, we'll get negative 6 root 6 minus 6 root 3. And I just want to double check that one. Negative 6 root 6 minus 6 root 3. Yeah, don't tell you guys the wrong thing. Number 4 isn't simplified because we got a radical in the denominator. How do we get that radical out of the denominator? Well, first I would look to simplify it, and 32 can be split into a 16 and a 2. 16 is 4 squared, so this can become square root of 6 over square root of 16 times the square root of 2 equals square root of 6 times 4 root 2. But the denominator is still not rational. I got this irrational number down here. So I can multiply by a form of 1. A square root of 2 will get rid of the square root, make this rational, but you got to balance that with the square root of 2 on top. This here becomes the square root of 12. Try to combine those, divided by 4 times square root of 2 times the square root of 2 is just a 2. Let's take a look at this. So I got the square root of 12 divided by 8. Well, that 12 still's got a perfect square root as a factor. So I'm going to split that 12 into a 4 and a 3. Make that now 2 root 3 over 8. And now I can divide the top and the bottom by 2 to just get the square root of 3 over 4. That one really simplified down. Something much smaller than this right up here. Not the only way to do that. We could have distributed the square root, simplified the fraction. But this method works. Let's look at number 5 over here. Number 5, it's got an irrational denominator because of this square root of 5 in the bottom. But I can't just multiply it by the square root of 5 because that would get distributed over here. Bottom's still not rational. The only method, if you got a binomial down here with an irrational part, is to multiply by its conjugate. Find the conjugate, you just rewrite it, but you flip that middle operator. And I can't just multiply that to the bottom. I have to multiply that whole thing to the top as well. So the conjugate over itself. This is now a very large, but still equivalent of 1. So it's not going to change the fraction, but it's going to rationalize that denominator. Let's distribute the 3 to the top there, and I'm going to get negative 3 minus 3 root 5. Let's take a look at what happens on the bottom. First times first gives me a 1. Outside gives me a plus root 5. Inside gives me a minus root 5. So those will cancel. And last, positive times a negative, so it's negative root 5 times root 5 is a 5. Square roots canceled out because it's square root of 5 squared. These also cancel out. Now what am I left with? Negative 3 minus 3 root 5 all over, well, what's 1 minus 5? Negative 4. I could make everything positive, divide the top and the bottom by negative 1. And I think that's probably what they did in the answer key. 3 plus 3 root 5 all over 4. That's my guess for number 5. 3 plus 3 root 5 all over 4. Very good. All right, let's see. Solve each equation. Remember to check for extraneous solutions. I'm just going to jump to number 10 here. If we can do number 10, we can do all of these. Radical equals a number plus a radical. This is our hardest type. In fact, I'm going to white out a couple of these so I just even have a little bit more space to work on number 10 here. All right, so I'm going to start by just copying it down. Square root of 2b minus 3 equals negative 1 plus the square root of 3b minus 2. When you've got 2 square roots, try to isolate at least one of them. You can isolate both of them, great, but at least this one over here is isolated. So I can get rid of one of my square roots by squaring both sides. Unfortunately, this other side becomes really large and complicated. And it might be worthwhile to do some rearrangements to avoid that, but it actually looks like this is going to be avoid big numbers in the best we can. All right, square root cancels. This side's easy. On this side over here, if you want, you can write out the intermediate step where you actually write out negative 1 plus the square root of 3b minus 2 times itself. I haven't even left room for that, but essentially you've got to FOIL this. It's only foiling because this still only counts as 2 terms, but here's what's going to become. First times first gets us a 1. Outside is going to give us a negative square root of 3b minus 2. Inside is going to give us another negative square root of 3b minus 2. And last, square roots will cancel out. I'll be left with just a 3b and a minus 2. All right, a lot of like terms to combine up here. 2b minus 3 equals, well, the 1 and the negative 2 can become a negative 1. These can be combined to get a negative 2 root. 3b minus 2, just combining their coefficients there, plus 3b. And now I want to isolate this radical by moving everything away from it. So let's add 1 to both sides. Let's also subtract 3b from both sides. Negative b minus 2 equals negative 2 square root 3b minus 2. Don't want to square it with this coefficient here. I mean, it's not the end of the world if you do. Let's actually do that. I'm going to square both sides now so I don't have to deal with fractions. This side over here becomes negative b times negative b is going to become b squared. Plus 2b plus 2b, just foiling this, plus 4. All right. Yeah, I think so. This side over here, distribute that square. This will become a 4 times 3b minus 2. And at least now all our radicals are gone, and we can just go to work on the quadratic. B squared plus 4b plus 4 equals, distribute that 4, 12b minus 8. Going to want to set this equal to 0 so I can use the zero product property. Subtract 12b, add 8, subtract 12b, add 8. Let's come up over here with it. B squared minus 8b plus 12 equals 0. Is this factorable? Two numbers that multiply to be 12 but add to be negative 6. I think that does work with a negative 6 and a negative 2. Which gives us our answers of b equals 6 and b equals 2 after I use factor theorem. But hold on, whenever we're solving, we've got the chance of extraneous solutions. So both of these could be good answers, just one could be a good answer, or neither could be good answers. We got to plug them in to see. So let's just kind of do it somewhat just out loud here. I'm going to plug in 6. 2 times 6 becomes 12. Minus 3 becomes 9. Square root of 9 equals 3. Negative 1 plus, I'm doing the 6, so 3 times 6 is 18. Minus 2 becomes 16. Square root is a 4, so this is 3 equals 3. That's a good answer. All right, let's just try it out loud with plugging in 2. 2 times 2 is 4, minus 3 is 1, square root of 1 is just 1, equals negative 1, plus 3 times 2 is 6, minus 2 is 4, square root of 4 is 2, 1 equals 1. So they're both good answers. I'm going to switch that to green. Neither is extraneous, both good answers. Problem number 10 there. And we should really just double check that one. It was a long problem. 6 and 2. Got them both. All right. Rewrite each expression in exponential form. Not too many ways you can mess this up, but maybe losing these parentheses here in this one and only applying that 3/2 to the x, or flipping this fraction around. Recognize here the index is 2, but it's got to stay at the bottom of that fraction. Radical form, even less ways to mess these ones up. Just make sure you put the index in the right spot, and whether you put that exponent inside or outside doesn't matter to me. Outside is safer though. All right. Simplify. Let's do 15. This will be a good one. So this, how we're going to simplify it is we're going to change it into radical form, make this the cubed root of 343 x to the 9th, all raised to the 4th. Cubed root of 343. I feel like that is a number I should know. Let's see. 5 cubed, nope, maybe 7 cubed is 343. That seems like it could be, let me just check the answer key. 15. Oh, well, then we distribute the 4. 7 to the power of 4, is that 2,401? Got a feeling that it is. All right, so the cubed root of 343, I'm going to say it's 7. If it's not, I'm sorry. Cubed root of x to the 9th is just x to the 3rd. We can make 3 groups of x's there. This is still all being raised to the power of 4. 7 to the power of 4 is, I just checked the answer key, 2,401. And then we multiply exponents here. So that gets distributed like that. That's where we get that from. Solving equations, let's try 18. First thing is I want to isolate this term with this exponent by doing simple things like adding 9 to both sides. 500 equals 4 times r plus 20 to the 3 halves. Simplify further by just dividing both sides by 4. Now what do I have? 125 equals r plus 20 to the 3 halves. And now we use the trick of raising both sides to an exponent that will cancel this exponent because of the multiplication property. Well, the exponent to an exponent property, which results in multiplication. Simply put, just raise it to the reciprocal. All right, on this side, that's going to cancel, or essentially just become a 1. Anything to the power of 1 is just itself. And now I've got the cubed root of 125 squared. The cubed root of 125, I do know that that is 5. 5 squared equals r plus 20. 25 equals r plus 20. R equals 5. For 18, r equals 5. All right, simplify, and it gives us this clarification here. Your answer should contain only positive exponents. So if we ever have an exponent that's negative, we'll just put it into the denominator and it will become positive. That's the trick to getting only positive exponents. Maybe we'll see that in one of these. They look pretty similar in complexity. I'm just going to do 19. Maybe it looks a little bit harder. I say I can cancel out a 2. Everything's being multiplied, so canceling is allowed. Any other canceling I want to do right off the bat? Nothing matches exactly, so I'm going to combine before I try to do any more canceling. Everything's being multiplied, so on the top, I'm going to add exponents when I multiply these a's. A to the negative 3rd times a to the 4th. I add those, I'm just going to get an a to the 1st, or just an a. B squared times b to the 6th becomes b to the 4th becomes b to the 6th. A squared times a squared is going to become a to the 4th. And b to the 3rd. Oh, there's still 2 down here. I'll lose track of that. Times b to the 0th just stays as b to the 3rd. Or we could just say that this became a 1. All of this is still raised to the power of negative 2. Now let's do some canceling. I'm going to cancel this a with one of these a's, leaving 3 behind. Cancel 3 of these b's with 3 of these b's, leaving 3 of those behind. Let's see what this looks like now. I've got b to the 3rd on the top times 2a to the 3rd, all to the power of negative 2. Well, negative exponents flip fractions, so I'm just going to deal with that negative right now by flipping this upside down and getting rid of the negative. But there's still the 2 there. And now that 2 can get distributed, but when it does so, be very careful. It's going to multiply that 3. It's also going to get distributed to that 2, and it's going to multiply this 3 here to give me 4a to the 6th over b to the 6th. Let's check 19. 4a to the 6th over b to the 6th. All right. Functions, operations with functions. Let's do a little bit of that. Perform the indicated operation. F minus g of 0, well, that's going to be the same as f of 0 minus g of 0. f of 0 means plug in 0 for t in that first equation. So negative 0 squared minus 2 times 0. G of 0 means plug in 0 for that second function. So minus, in parentheses now, 4 times 0 plus 1. That cancels, that cancels. The negative gets distributed to both of these, but that's just a 0. And to that 1 there, we get a negative 1. 21, I think we get a negative 1. We do. Let's do a composition here. I'm liking the looks of 23. G of f of x plus 1 is how we would say that. So what does this mean? Well, it means that we're going to do f of x first. Our input is x plus 1. It needs to go into, we read this backwards, f of x first. And what's that going to give us? Well, f of x takes the input and multiplies it by negative 2 and adds 1. So this is going to give us negative 2 times x plus 1. Our input is the expression, plus 1. This can be simplified to negative 2x minus 2 plus 1, further simplified to negative 2x minus 1. And now it's time to take that and plug it into g of x. G of f of x, we do f of x first. I simplified it and plug it into g of x. G of x takes the input, squares it. So the input is this whole thing here, negative 2x minus 1. It's going to get squared, and then we're going to add 3. And just for posterity, we should simplify this. Negative 2 times negative 2x, that's going to give me 4x squared plus 2x plus 2x plus 1 plus 3, 4x squared plus 4x plus 4. 23, I could be way off on this one. 4x squared plus 4x plus 4. Got it. All right, always exciting. So yeah, try 24 now. Good way to get ready for composition of functions. Now we just got to sketch some graphs. We're going to do this by using transformations. Our parent function is just this kind of half of a sideways parabola. It looks like this, 0, 0, 1, 1, 4, 2. The next perfect square would be 9. It's just off the graph, 9, comma 3. So that's our parent function. And we'll just focus on those 4 points. And we're just going to transform them with the transformations that we see. The transformations that I see are this plus 4 is going to move us left 4. This minus 5, even though it's in front, still is functioning as that k value. It's going to move us down 5. And this 3 in front is going to do a vertical stretch of 3. And I got to do the vertical stretch first. So every point gets 3 times as tall. 0 stays in the same spot. This one was 1 tall, now it's 3 tall. This one was 2 tall, now it's 6 tall. This one was 3 tall, now it's 9 tall. Now it's way off the graph up there. So this is not our final function, it's just an intermediate. Now I've got to move all of those points down 5 and left 4, and that will give me my final function. So here's, I'll start with this first point. Down 5, left 4, 1, 2, 3, 4. Got a point right there. Down 5, 1, 2, 3, 4, 5, left 4, 1, 2, 3, 4. Got a point right there. This point here, down 5, left 4, 1, 2, 3, the lands right there. This point here, down 5-ish, left 4-ish, I don't know about there. Yeah, we got the shape. That is our final function there. Let's compare that to the graph. 25. Yeah, it looks about right. I'd be able to pick it out of a lineup just based off those transformations and what this graph looks like here. Oh, we better do this cubed one. With the cubed one, your parent function looks a little different. The cubed root of 1 is 1, but our next cubed root doesn't come until 8. The cubed root of 8 is 2. Cubed root of -1 is -1. Cubed root of -8 is -2. So this one it reaches all the way across the graph, and it's got this kind of curved S shape. And now I've got to apply my transformations. This is a left 1 and a down 5. Pretty similar to our last one, left 1, down 5. With all of those points I just put on there. Left 1, down 5 takes us to about there. Left 1, down 5, left 1, down 5, left 1, down 5, left 1, down 5. Looks about like that for our final graph. 26. Again, doesn't have to be perfect. I could pick that out of a lineup just by seeing that the transformations are in the right spot. All right, well, we'll call that good for this homework help video. Hopefully this has been helpful, and have a good rest of your day.